if you are not a member of the BCS and you would like to join, you can get a discount by coming to this event. So you need to use the code BCS NOTS with 2 T's 20 when you sign up, and that should give you a 20% discount. And just finally, before I pass on, is, oh dear me, really not doing very well with my mouse tonight. There we go. Next event we've got is on the 17th of July. So this is a kind of slightly longer event than we normally have, and this is an in-person event. So it's our summer social with 3 talks from Big Spark around data and enterprise architecture. We're hosting this at Trent Bridge. So I don't know if I put Trent Bridge in, it's not Trent Bridge in, it's actually Trent Bridge, from 6 to 9 p.m. on the 17th of July. There will be refreshments from between 6 and 7 and a chance to socialise and network. And then the talks will be on from 7, and there will be a Q&A afterwards. So if you want to come along for that, we'd love to see you. You can meet some of the committee and hopefully maybe want to get involved with us next year. If you're inspired by Andrew tonight to want to do a talk yourself, there's a link to a form you can complete letting us know what you want to talk about, and we will get in touch with you about future events from September onwards. Okay, so that's it for me. I will stop sharing and now pass over to Andrew for his talk.
Ooh, thank you very much. So I will just start sharing, and can you all see that?
Yep, I can see it.
Perfect. So thank you very much for the introduction. So yes, as said, I'm Andrew Swirsky. I'm the managing director of Beetlebox, and today we're going to be talking about automating for a tiny future. Or a bit more long-winded way of saying it is accelerating embedded device development with BeetleboxCI Enterprise Edition. So automation isn't going big, it's going small. To highlight what I mean by this, I'm going to talk briefly about what's happening in the world of artificial intelligence. So when I originally wrote the abstract for this talk, there was this general feeling of AI going big. It was in the name, it was even in the name, large language models, or LLMs. The LLM ChatGPT had been out for a few months, which was based on GPT-3 that had 175 billion parameters. And that, although not officially disclosed, it was rumored that GPT-4 had multiple times the parameters of GPT-3. The current thought at that time was that we would have these relatively simple machine learning models that just had to be fed massive amounts of data and be really, really large. And we were going to be seeing 100 trillion parameter models soon. But this line of thinking didn't turn out to be true. We can most distinctly see this with Google's newest LLM, Palm 2. The original Palm 1 had 540 billion parameters, and Google claims that Palm 2 is significantly smaller, yet outperforms the original model on a variety of tasks. In their paper, they hint that it may be between 100 to 200 billion parameters, which is comparable to GPT-3, but with performance that is equivalent to GPT-4. Even more surprising was that Google announced that the smallest version of Palm, called Gecko, was actually capable of running on a mobile device, so it would even run while offline. And the reason for developing these models is quite simple: cost. If internet search users come to expect AI-generated content every time they search for something, this will require a huge amount of scaling in terms of Google servers. And if any company can get these LLMs to run on tiny, cheap, and power-efficient devices, they can develop next-generation AI without exorbitant costs. In other words, there's going to be a huge demand to run these AI on devices, and it won't be limited to just smartphones. It'll be a range of consumer devices, from smart TVs to the entertainment systems running in automotive vehicles. So this is why at Beetlebox, we believe in the future of not just tiny AI, but all sorts of smart applications running on embedded devices. As the founder and managing director of Beetlebox, Our mission is to empower companies working with embedded technology to develop sophisticated software without compromising time or product quality. Ultimately, we aim to deliver a solution that can take code developed by teams of engineers and automatically place and run that code across thousands of embedded devices to ensure proper functionality and bug-free code. These systems can be used for everything from early detection of bugs at the beginning of development to running updates to devices that will be with customers for the next decade. So in this talk, I'll shed light on the unique challenges to device development and how our solution, BeetleboxCI, addresses these problems. We'll explore real customer success stories and delve into the intricacies of our solution, powered by our proprietary continuous integration tool. And lastly, I'll share more details about how to get involved with customers. So now we've established why we believe that companies will continue investing in embedded products. Let's delve into the unique difficulties faced when working with these embedded technologies. After all, what company that works within embedded devices wouldn't want to have the ability to have code automatically placed and run across hundreds of devices? But turns out there are large hurdles of developing these sort of test systems that restricts them. Developing for devices comes with its own unique set of challenges that requires innovative solutions. And at Beetlebox, we understand these challenges firsthand. So let's dive straight in. Perhaps the greatest challenge is time to market pressure. When you're developing embedded products, there is a need to release within tight deadlines. This puts a lot of pressure on development teams to get the product out, and everything that does not move the product forward gets pushed to the wayside. A project manager may want to adopt automatic testing, but then they will realize that you need to adopt a bunch of new open source technologies, hire in experts, or develop the expertise in-house, and then combine that all together into a single functioning system. This is all before they can even start testing the product. And when faced with this problem, project managers will scrap developing an automated system in the favor of focusing on the product itself. And what compounds this problem is the complexity of the testing requirements. Embedded systems are a mix of hardware and software components that need to be developed simultaneously. On the hardware side, the hardware will be made in prototyping batches, while software development happens in a more linear fashion, as you don't need to wait for manufacturing. If you want to automate this process, developers will need to come up with ways of connecting prototype hardware as the batches arrive to a system, and that as batches arrive to a system that can register and run your software on these new prototypes. So this is a huge requirement when it comes to building these systems and often results in failure. And this nicely leads into the third point, which is where there's a scalability problem. In regular software development, if you want to run more tests, you just rent more machines off the cloud. In embedded development, you've only got a limited amount of devices from those batches. This makes running high amounts of tests simultaneously a difficult problem, and any idle time is essentially a wasted opportunity. So on top of all this, early bug and performance detection is even more critical than it is in normal software development. When a bug occurs, you need to be able to tell if it's on the hardware or the software side. Hardware bugs can be extremely costly to fix late into development, so it's crucial to root them out early and have them fixed by the next batch. Performance detection of software is also critical for choosing the right hardware. For instance, if you're planning on using machine learning, you may choose to use the NVIDIA Jetson series, but what chip do you exactly need? How much computing power does your machine learning model need? How much heat will that model create? Will the model you've chosen meet the feature requirements of your device? All these questions can be answered through early performance testing. And I've been talking a lot about these problems of automated testing, but it's worth remembering why we can't just go for the alternative, which is manual testing. Manual testing is prone to human error and is inefficient. If the development team is running tests by human constantly, repeating the same test, it's not efficient for that person. On top of that, we introduce human error into the testing process. And can we ensure that every time this test is performed, it's performed correctly in the exact same way? And finally, we have regulatory compliance. While most software development does not have strict regulatory requirements, many industries in the embedded space do, such as automotive, medical, and aerospace. This is where most of the development time is actually spent, and it's crucial to have in place a comprehensive testing solution when engineers can easily tell if the requirements have been met. So it's our first-hand experience of these problems that drove us into looking at how we could smooth our development operations, or what's known in the software industry as DevOps. We looked at the market and realized there was no exact product that fitted our need, only products that required weeks of tinkering to fit what we wanted them to do. And after years of development, we came up with BeetleboxCI. It's a complete solution for developers to streamline their embedded testing from setting up a hardware installation to software delivery. We do this by combining our experts' services with a proprietary DevOps technology. Unlike competing DevOps software, we have designed and created our own continuous integration tool called BeetleboxCI that is designed to easily create large-scale systems of interconnected embedded devices that can be automated through a single server hub. And as a company, we are also experienced in understanding not just the technology, but the business context of these systems. We work with our customers to understand what their business needs are and how our solution can deliver real-world value to those to our users. We then help our customers with the creation, training, and ongoing support of these large-scale systems. So let's now take a deeper dive into how our solution works. Essentially, our solution is a mixture of both hardware, software, and good software development practices. We encourage developers to adopt continuous integration, where developers frequently merge their code that they are working on onto a single central repository. This can be very difficult to what embedded developers are used to, which is normally working in a more siloed environment. But adopting continuous integration is key to routing out errors early in the development process and improving software quality. Each member in a development team is encouraged to submit the code into a central code repository at least once a day. BeetleboxCI supports Git, as well as having specific integrations for GitHub and GitLab. Once the code has been submitted, Beetlebox can automatically detect the changes and begin the automated building and testing process. Let's say our developers have put out new code that they want to update devices that have already been released to customers. Using BeetleboxCI, developers can create an automatic pipeline that runs through all the tasks needed to ensure safe, bug-free releases. The first stage will be for the software to be compiled together on a central hub. This central hub can either be an on-premise server, as shown here, or it can be a cloud provider such as AWS. Once the code has been built, we can first test that code by running software-based emulators that copy the software environment of our embedded device. By doing so, we can find bugs in our code before even a single piece of actual hardware has been used. After emulation has succeeded, there are typically two different setups that our customers like to use. The first thing is they want the ability to run thousands of tests across hundreds of different devices to get results quickly. To do this, we work closely with the customers to help them create a device farm. This is where we connect racks of embedded devices to the central hub. Normally, the creation of these farms and getting them to communicate with automated software is incredibly time-consuming and difficult. But using BeetleboxCI, we have streamlined this process. We can easily register these devices with BeetleboxCI, which can then communicate with these devices using several different protocols. For instance, we can communicate over Ethernet or even via USB. When devices are used as part of a device farm, they can become incredibly efficient. Developers may only have access to a limited amount of devices, so it's important that they have minimal idle time. This is achieved by developers constantly pushing their changes through, which will give them quicker feedback and flag any errors or performance issues. Developers can even run deeper tests on scheduled overnight or weekend tests, which can even give better insights. The second setup we have here is in-lab testing. Much of the time, embedded devices need to be tested using certain sensors or need to be connected to a certain probe in order to get a reading out of it. Previously, we discussed that manual testing can introduce problems in terms of human error or consistency in experiments. Using BeetleboxCI, devices in lab can be connected to ensure the experiments are run in the exact same way every time. On top of that, sensors and measurement equipment can be connected back to BeetleboxCI to ensure that all results are properly logged. Through both in-lab testing and device farms, developers are able to plan the safety requirements for their system and then run tests to ensure those safety requirements are met in a pass-fail way. And finally, once the development team is both satisfied with the device farm and in live testing, BeetleboxCI can then deploy out to devices that are in the field. We want to encourage developers to also adopt continuous deployment, which is where devices are able to be updated incredibly frequently so that features can be rolled out as soon as they are available, and also so that developers are able to gather real feedback to inform the next update. BeetleboxCI is able to interact with over-the-air update systems and ensure that these updates roll out the exact way that developers want. And at Beetlebox, we make setting up these important automated testing platforms both efficient and affordable. Developers can adopt these efficient methods without the painful time barriers that were involved before. So yeah, to quickly summarize the key benefits, we improve developer productivity through accelerated development time by reducing testing cycles and time-consuming manual tasks. We enhance product quality through comprehensive hardware-in-the-loop testing and simulation. We ensure early identification and resolution of software defects, minimizing risks and ensuring robust end products. We allow focused engineering efforts that increase efficiency and cost savings by automating testing workflows and reduce the need for physical tests. And we create powerful automated tests that improve scalability with the ability to run tests across hundreds of devices simultaneously with end-to-end tests. So let's now look at BeetleboxCI in action. So one of the first uses of BeetleboxCI was when we were developing video processing for robotics platform developed by Sundance Microprocessor Technologies. Our basic objective was to develop a video stabilization platform that could take shaky video that cameras in robotics often gave and output a smooth video to the user. To do this, we used a field programmable gate array or FPGA device. These chips are rather unique for the fact that their hardware is actually reconfigurable, which means that you're able to create highly optimized algorithms that can transform the video stream. So to show how the algorithm works, we can look at the image with these various clock faces on it. Basically, this is a timeline of a shaky video, and the red line at the top represents how the clock face moves up and down with the shakes of the camera. To smooth itself out, we basically look at the first frame in a video and notice any key points in that frame. This could be the corner of one of the Roman numerals or one of the sides of the clock tower. We gather hundreds of these key points and save them all. We then look to the next frame, and in our case, our next frame is at t = 10, and we gather the key points from that again. We can then match the key points together and see how they have moved between frames. And by comparing these movements, we can then build how the camera is shaking, which you can see in the upper figure in blue. We can then apply a smoothing algorithm to find a better, smoother camera path, and then reapply that to the video. At the bottom, we can then see the same video again, except this time with a lovely smooth output where the red line is not moving up and down constantly. So using BeetleboxCI, we're able to build a system that could take various different video clips and run that through our FPGA. We are also able to constantly check on the power used by our device to ensure that we are gaining a competitive advantage over other chips. Our end result was a system that was able to meet the power requirements of the robotics platform than what we have achieved if we were using more conventional chips. So now I have a quick demonstration of our technology using that case study. Our setup was a classic in-lab case. We had a central hub connected through to a ZU104 board that contains the Xilinx MP-SoC FPGA chip that we wish to test on. The MP-SoC can be quite challenging to test with because it both contains a CPU and an FPGA fabric on the same chip, meaning that when you run FPGA simulations, and you have to do that on top of Linux-based emulators, to see how these two systems interact with each other. So for this particular project, we use GitHub as our Git repository. We develop code locally that would run on our computers and then push that code through every day. Where the configuration files that tell BeetleboxCI what to run is then held in this .bbx file, and the rest of the source code is held throughout. We can see that in the source code that we both run emulators. So we have a software emulation and hardware emulation, but we also have code that actually runs the hardware itself under the code folder. So from the BeetleboxCI interface, we can see all our different projects and automated pipelines that are running. We are also able to monitor computer usage as well as the different files that we have generated by our pipeline. We have called our particular project, this particular project, brief hardware run. So you can see it at the bottom there when we have 2 tests that we're running. So let's now dive into that pipeline. So each Git repo is associated with a particular pipeline. That pipeline will read and write to the configuration files that are held in that Git repository, and it can gain access through the authentication settings when you create a project. Using BeetleboxCI, you can also edit the configuration field directly, and all these edits will be saved to GitHub. In Beetlebox, each pipeline is essentially made up of what's known as a series of workflows. These workflows then break up into individual jobs, which are the basic building block of each pipeline. Each job contains a series of sequential steps that must be executed in order for a job to pass successfully. For instance, we could have a job for compiling our software and then a separate job for running a simple test on that compiled software. Each job runs in an isolated, clean, containerized execution environment known as a runner. BeetleboxCI will also automatically run as many jobs in parallel as possible and assign the right computing and memory resources to each runner. And files can then be input to the job, and resulting files are outputted as what's known as artifacts. So using BeetleboxCI, we're able to monitor in real time how each pipeline is running. We also provide a full history of each and every run that has occurred in the past and are able to manually trigger each workflow from the UI. You're also able to separate each of these pipelines by branches in your Git repository. So in each job page, we get a detailed breakdown of each step, along with the computing and memory resources used for that particular job. This particular job had 3 steps: create container, download artifacts, and run hardware. We can see the output of each step in the log file. The run hardware step in this particular example would take the generated files from the previous steps and place them onto the FPGA. It will then run a simple test on the FPGA board itself, and we can see that the results of this are passed. So we can move on to, so we can call this pipeline successful, and then potentially release. So if you're interested in learning more about how Beetlebox can be applied to your systems, we have a simple process. First thing we normally do is arrange a phone call where we can help understand what your use case is and understand the your wider business case. Working with you, we will develop for free a proof of concept that can take a small valuable section of your development process and automate that. This typically tends to be connecting and running tests on a custom board. If you're happy to move forward, we put together a full-scale solution for your systems. Our team can then move forward with a full onboarding process, including any setup, training, or support that is required. Finally, we provide ongoing support for your solutions. So if any of this interests you, please feel free to get in contact. We're always more than happy to talk about your requirements. Thank you very much for listening to my presentation. I'd be happy to give any answers to any questions that you may have.
Thank you, Andrew. I have a question from Paul, and he's interested to know if you could detect the enemy within additional malicious functionality. So that's what he's asking. Paul, if you want, you can. I think you have your microphone and mute, so I think you can ask the question directly.
Yeah, only because I'm not familiar with your tool set. As I say, it's just I was in a separate workshop, not to do with your tool, and I raised the same question. So you might write bug-free software. Just interested, I suppose it comes down to every company's method of how they actually review the code that's been written by the developers. I spoke about a hypothetical situation where I was in 20 years ago, where I could get past all of the normal change procedures and put in code which was bug free, but over a period of time could actually cause a lot of damage to company systems. So it's more about a case of, does your testing regime actually spot things like that?
So when we work with developers, so in that case, we don't like define what exact tests they run. That's kind of for the customer to decide what they want to do. But if they're saying, okay, how do we attack the enemy within, we normally suggest to them a V model solution. So for them we'll go over like exactly what this, we'll go with them to define what exactly the system requirements are, and then eventually break that down. We'll break those requirements down into exactly how do you get those requirements into a pass-fail state. And if we notice that we have the slippage, like you say, like in the future, it starts doing damage to our systems, then something's gone wrong actually at that requirement section. So we can review that and say, okay, why has there been the slippage? Or can we develop tests that test for slippage? I think a really good example of this is actually within machine learning, where if you use old data that's too old and you try and apply that to new data, it just fails automatically. So within your requirements section, you need to have something that says, okay, we need to make sure that we're only like the freshest of data. It must be within 2 to 3 months of before to actually be applicable to our situation. And what we can do is help work with those developers to develop tests that make sure that it fits within those 3 to 4 month, it meets that 3 to 4 month requirement. So did that answer your question then?
It did, but I suppose the proof of the pudding's in the eating.
Yeah. It's like if you're interested, like always talk to us. We're always we're always happy to chat, and then you can see the pudding.
I do have a question. What is your advice for companies that are using this embedded system and they don't even realize that they need these types of tools because they exist?
Yeah, that's actually, I'd say that's probably our number one problem when we talk to people, is that they don't even know that sometimes they don't even realize there's an issue. Because if you don't, it's more, sometimes people need education on what continuous integration actually even is, right? They're still following, the models from the 90s, right? They're still following waterfall models. So we need to say, actually, in the software development world, things have progressed. We've been using continuous integration for a number of years now, and here's how it can work. And more importantly, here's how you can actually apply that to embedded software development. And from there, it becomes a process of, okay, once you've got, once you're actually got developers who aren't just siloed and working by themselves anymore, and are actually working as a group and submitting to a code repository that is being regularly tested, at that point, the need for automated testing becomes very, very apparent. So I'd say, obviously, if they won't talk to us if they don't know they have a problem, but sometimes people come to us with a very, very small problem. Like I've had people who've come to us because they can't connect a jumper together, like automatically. And that can actually lead into a deeper conversation about how you're testing. And so I think maybe coming at it with they'll come to me with a small problem, but then we look at what they're doing, we realize there's kind of larger issues about what they're doing.
What are your thoughts about your platform running with Docker to emulate specific architectures and then deploy the Docker container on the device that supports Docker containers?
Yeah, so our software is actually built on Kubernetes. So we have sort of native support for Docker, although it's a bit complex because Docker separated. Kubernetes used to natively support Docker, but then Docker split into Containered, which is an open source solution, which is now natively supported by Kubernetes, I believe, right?
Yeah.
So what we're able to do, so it's something that we're looking. It is something we're looking into doing, which is actually being able to run containers directly on device itself. But the problem we have with that is we don't want to be too. We need to be very agnostic as to the way that developers do things, right? Because for some people, running a container on a device would be a great benefit for them, especially if they're running, like a powerful, some sort of powerful robotics platform. But we also want to deal with the situation where they have, a tiny microprocessor, maybe a Raspberry Pi Pico, which we've been testing with recently, and where there isn't even an operating system. So it's like, okay, how do you have a software that can both have it so you can deploy Docker onto devices, but also have a software that is agnostic enough that it can even test things that don't have an operating system on them. Yep. It's a fine line. And whether we'd recommend people to run Docker, I think that depends. It's more of like
on the application.
Yeah, on an application. Like I said, it's perfect for robotics platforms. I'm not sure how people would feel it on a regulation.
Hi, I need to...
Yeah.
Oh, sorry.
Sorry.
My apologies. Okay, thank you. I think you've covered very well those questions. I'd like to invite attendees to ask your questions. I've been monitoring the chat, and I'm more than happy to take your questions.
I'm just going to ask a quick question while we see if anybody else is typing anything. It's kind of, yeah, it's more it's asking if you would be interested in something. So one of our colleagues, we have a large number of FPGAs at work, which actually used to be part of Pedro's research, and one of my colleagues is looking at repurposing them and offering a kind of a test bed as a service on them. So we'd have a kind of a remoting into them, configuring them. And I just wondered if you'd be interested in talking to him about any kind of potential collaboration, or whether it would be something that you might kind of want to use or offer to your clients as well as an alternative.
Yes, it's perfect time to talk about academic projects, actually, because we are currently working with Pedro actually already on some of his recent research projects. So when it comes to academics, we're always more than happy to reach out and help in any way we can. Because for us it looks great. We give our expertise, and then normally we're happy to like generate a bit of buzz about what we're doing and extending our help to the wider community. When it comes, I can talk specifically about your case because it's an interesting one where FPGAs as a service, because it's been attempted before. I think the most famous one is probably AWS's F1 instances. The problem you have with it is really malicious users. So maybe not to go too much into technicals of it, but there is, even when I was back before I started, when I was working at Beetlebox, we looked at this when I was doing some research, and is what happens if the user starts making, oscillators in your FPGA that just constantly are flipping bits and trying to generate as much heat as possible, essentially. So the problem is that you need to put you have to put restrictions on what you have to. It becomes complex because once you start considering that, then you have to do things where you have to reconsider how to test to make sure that the system is not malicious and all these it's not being exposed to the public. The problem becomes a lot simpler if you have a select amount of private users, in which case you can expose it and be quite happy, and we can work with you on that. And yes, so we have So let's just say we've thought about this before. We've had a lot of experience with it, and we'll be happy to chat about like all the specific difficulties you might face. Yeah.
Fantastic. Yeah, we're just in the kind of way of the situation of kind of investigating whether there's a market for it, what that might be, what the restrictions might be, what we need to put in place. So I think it would be great for you to have a chat with my colleague John Robinson about it. Then I'll drop you an email with his details.
In fact, Bev, we could invite Andrew to attend the showcase.
Absolutely, yeah.
Ooh.
So yeah, on the 3rd of July, and this is for anybody else that might be interested that's in the audience as well. So we're going away from BCS and onto NTU, I'm afraid. So I hope you'll excuse us for that. On the 3rd of July, the Department of Computer Science at NTU are hosting an industry showcase day, and this is to kind of encourage kind of connections and collaboration with employers and people from industry that might come in and get involved in projects. They might be interested in apprenticeships. There might be some kind of knowledge exchange that want to get involved in, or just kind of have a conversation and help us to discuss our kind of curriculum as we move forward. So if anybody is interested, I guess I can post, if people don't mind, I can post the link to the form in the chat. And yeah, I shall find that.
Yeah. But just the concept of FPGAs as a service, it's a lot of people have attempted it. And it's an interesting one because on the one hand, you have like AWS's idea with F1, but then Microsoft they've taken a different approach to it because they have a thing called Project Brainwave, which was when they were using FPGAs to power Bing. I'm not sure what's happened now that they've got like the LLMs on Bing, but they had FPGAs running on Bing, and then with Azure they opened it up so that you were able to run machine learning models directly on FPGAs, but they restricted it to just being machine learning models, if I remember correctly. So yeah, it's an interesting problem how you do that safely. FPGAs give so much freedom that it becomes quite difficult to manage what the user is doing. It's one of the downsides.
Okay, thank you very much.
Yeah.
If I can add to that, I've been trying to explore. So Intel has partnered up with Microsoft Azure, and they give access to their cloud, which includes FPGAs via Azure. And you have, for example, Xilinx, AMD Xilinx, that they are giving access to their infrastructures to Amazon AWS. Both of them are working very well, but it's mostly for academics, as far as I'm aware, because of the pricing. So I think they are sensing the market, but
it's not just pricing, because there's obviously areas where people are very happy to throw money, right? So let's say finance, for instance, right? If you could have it so that there'll be a lot of people who would be very happy to have the high-speed finance algorithms be sitting on the cloud rather than them having to sit them in their own personal servers and hire a bunch of hardware guys to having to maintain them. The issue is that you have these interfaces. So because you can't just directly expose the FPGA to the cloud because it opens you up to problems. So what you have to do is you have to put this interface layer in between them. Normally you have a CPU that will sit between your FPGA and what you're communicating with. But the point of FPGAs is high performance. So if you have these interfacing layers, then suddenly you're losing the performance. And that's a big difference in the FPGA world. Yeah. And I think it's a real shame because it's one of the reasons why I think that GPUs just took the edge to FPGAs. It's just because GPUs are so much more cloud friendly. Yeah.
Okay, I'm going to quickly scroll to the chat. I don't think there is too many questions today. So, Bev, back to you. You're mute.
Sorry, unmute. I've done that for a while. Yeah, thank you very much for your talk, Andrew. It's again very, very interesting. Thank you to the audience. I hope you found it interesting. I hope you got something out of it. As I mentioned at the beginning, please do kind of connect to us on LinkedIn. Maybe consider joining the BCS if you're not already a member. And if you can join us on the 17th of July, I think the booking will be open fairly soon, and it would be good to see some of you there. So otherwise, yeah, if Paul's clapping, if we could thank Andrew for his time, and I hopefully see some of you soon.
Thank you very much.
Thank you so much. I just dropped a URL showing where the video is going to be available over the next few days. Okay, so again, I'd like to thank you so much for attending today's session, and I look forward to the next event, which, Bev, I believe that is face-to-face, right?
Yes, 17th at Trent Bridge Cricket Ground, not Trent Bridge Inn, Trent Bridge Cricket Ground.
Okay, thank you.
Yeah, thank you.
Bye-bye.
Bye.
Bye.